Hello everyone, I am Ruonan. I will give a brief presentation on our paper TEDdy Efficient Large-Scale Dataset Distillation via Taylor-Approximated Matching, which was accepted by 18th European Conference on Computer Vision ECCV 2024. We are from the Learning and Vision Lab at the National University of Singapore. Currently, there are many challenges in DD. The most direct one is the scaling up problem. From the definition of DD, it relies on a bi-level optimization algorithm. For each iteration, a novel model is trained on the synthetic dataset in the nested loops, and each update for the synthetic data should backpropagate through an unrolled computation graph, which results in high memory and time complexity. Thus, for large-scale dataset, it is impossible to generate the synthetic data directly from the definition of the DD. Based on that, our method decouples the bi-level optimization and avoids inner-loop training. So how do we do that? Still, let's start with the traditional DD. It should be noted that in practice, we generally train more iterations in the inner loops. So training loss in inner loops is basically close to zero. Here, we iteratively apply the first-order Taylor expansion to the first term. The optimization objective is transformed into the sum of the gradient matching of the distilled data and the original data for all steps along the training trajectory of the student model. By this point, the computational efficiency has been improved, but it is not enough because computing the sum of gradients still requires a lot of resources, and there involves a second-order optimization problem, which may cause high computational complexity. So we do another approximation. Here, we prove that under the constraint, gradient matching is equivalent to the first-order and the second-order statistic information matching. So here we get the statistical matching for the synthetic dataset and the original dataset all step along the training trajectory of the student model. Still not enough because the process of training a new model at each iteration and calculating the statistic at checkpoints for each step still imposes significant computational demands. Then the next step is to solve this problem. For any segment of the training trajectory that starts at B and ends at B plus E, we again apply Taylor approximation. We find that the single-step gradient on real dataset comparable with multi-step gradient on synthetic dataset, which means we can replace segment trajectory of student models with a single teacher model. Also, catching the teacher model for head can avoid retraining model at each iteration. However, here comes another question: how to choose the teacher model. Here we calculate the distance between the teacher model and the student model at each stage, which, as we can see, basically matches the variation in the final results. So here is our optimization objective. Here we have used running mean and variance stored in the batch normalization layer instead, because this is very difficult to compute for a large dataset. We match the mean and the variance of the synthetic data and the original data over features based on different teacher models, and also the classifier constraint we mentioned at the beginning. For more theoretical analysis, please refer to the supplementary. Here we propose two efficient model pool generation strategies, the prior and the post-generation, corresponding to two practical cases. Both strategies can generate the model pool from one single base model. In summary, we propose an efficient large-scale dataset distillation method, TEDdy. We first generate model pool from single base model using two efficient model pool generation strategies according to the state of the base model. Then we follow our proposed optimization objective to update the synthetic dataset, which only requires a first-order optimization process. Here, considering the weak teacher models may mislead the data generation direction, we generate soft labels via weak teacher ensemble, which provides more richer label information expressions. Here are our experimental results. We achieved state-of-the-art performance both on downstream tasks with the same architecture and on cross-architecture tasks, surpassing previous methods by up to 12.8% and 13.2%. In addition, we conducted ablation studies and evaluated the efficiency and applied it on the continued learning, all of which demonstrated the superiority of our method. Thanks for your listening. If you'd like to discuss further, please feel free to email me.